Okay, this video is going to go over the electrophilic substitution mechanism for benzene. Really, the main or the only one of the substitution reactions you have to look at for this mechanism for benzene, electrophilic substitution, can also be referred to more specifically as the nitration of benzene. So you add NO2 to benzene. Benzene, again, is mostly going to show up on the IB exam as this hexagon with the ring inside of the delocalized electrons, but in a more condensed way, you can say C6H6. And when we're done with this reaction, we're going to have the ring is still there, the delocalized electron is still there, but we're going to have NO2 attached. And so in its what we've lost is an H, and so that H is going to be gone. So the final product, or what's known as nitrobenzene, is this compound, C6H5NO2, and the H plus will leave. So that's the substitution. We have an NO2 substituting for an H. That's why it's called substitution. And the benzene ring provides this ring. Remember, this ring is delocalized electrons. So that's the electron-rich species, and that's going to go out and attack electrophiles. And in this instance, the electrophile, the thing that likes the electrons or is electron deficient, is the NO2 plus. So the delocalized electrons will go out and attack an NO2 plus. And they're going to substitute on to make NO2, and we're going to kick off H plus. So why don't we start there, since that's kind of the simplest part of this whole thing. The overall reaction is that we start with benzene, and the electrophile is something called nitronium. And afterwards, we will have C6H5NO2, and we will have H plus. So the NO2 has taken the spot of one of the H's on the benzene ring, and the H leaves as an H plus, and the delocalized electron ring is maintained in the end. Okay? Now, what you actually need to do this reaction, what gives you this NO2 plus, which is an ion we haven't really seen much before, is you have to use nitric acid and sulfuric acid together will create this electrophile NO2. So sometimes they're called a nitrating mixture. So what happens is, if you start with HNO3, which is nitric acid, and H2SO4, which is sulfuric acid, to a certain extent, to a small extent, that's why we use double arrows to represent equilibrium, the sulfuric acid will give protons, donate protons to the nitric acid. That means the nitric acid has now gained an H plus, and the sulfuric acid has lost an H plus. So that's the first step. And then the H2NO3 plus can actually break down once it has that extra proton, that extra H, and it breaks down into the NO2 plus. And if you look at what's left over, there'd be two H's and an O. So that makes water. And the HSO4 minus stays as HSO4 minus. So this is how NO2, this electrophile, gets created. And now I have seen on the IB exam them asking for you to show the formation of the nitronium ion with chemical equations like this. You don't really need to show it as a mechanism, but I'll just simply show this one, H2NO3. H2NO3 has these two OH groups off of it, and overall it has a positive charge. And through sort of a chain of electron donation, essentially one of these things, or I guess I should have circled, let's go back. That group is going to leave as water, because it's quite a stable molecule, it'll break off. And then these electrons here will fill in this spot between the N and the O, and we'll end up with NO2 positive. So you don't have to show this part with the structures drawn out, but it's just that this structure, when it is H2NO3 positive, has these two OH groups in it, which basically end up in net effect of reacting with each other and forming a water molecule, which leaves behind an NO2 plus, which is the 2 double bonds between N and O. So that's how we create the nitronium, and then this is the simplified reaction for what happens between benzene and nitronium. The overall reaction, if we want to write it with those other chemicals, is that nitric acid is considered to be the other reactant, and H2SO4 concentrated is sort of the condition or the catalyst needed. And I believe we're going to run this one at 50 degrees Celsius. So when we run this, in the end, we know that we make the nitrobenzene. And if we know that we're kicking off H plus is how we think of it if we kind of simplify it. And then we look back here at the nitric acid. If I take NO2 out of nitric acid, that still leaves me with an O and an H left over. And then I've got the H that I'm kicking off of the benzene. So I've got 2 H's and an O. The other product will be water. So if we write it this way, then the other product is water instead of just being H plus, because nitric acid, oops, I'm still on a race. Nitric acid has an extra H and an O compared to NO2 plus. So it's just 2 different ways to write the same chemical reaction, this nitration of benzene. One is just NO2 plus and one is HNO3. So you kind of have to read the question to see which one they want you to use. And then the mechanism. So how does this actually take place? Well, it's going to look a bit like some of the reactions that we've seen before, the other substitutions as well as the other electrophilic addition reaction to a certain extent. Fewer arrows than the addition reactions, but some things in common with it. So here's our benzene, and here's our NO2 plus. You can just keep it this simple. You don't have to draw out the structure of the NO2 plus. The key is that in the first step, the electron-rich ring of delocalized electrons donates electrons to the N of the NO2. So that part has to go from the ring to the N. That's going to be a really important point. Then we get to a point where we have a carbocation intermediate. That should be a pretty common term by this point in the unit. I tend to connect it up here. So now you show that that NO2 has bonded on. Now, you can do this all along, or you can start to do it now. That carbon also had an H attached to it. All of these carbons have H's sticking out of them in benzene. It's C6H6. But when this happens, what we've done is we've messed up that delocalized electron ring. By forming this extra bond, we've messed up the arrangement of the parallel p orbitals. So the electrons are, for a moment, no longer delocalized. So this is the starting point. And then in the next step, we have to show that that ring gets repaired. So at this point, we need to show that the bond between H and C is going to repair that delocalized electrons, and that's how the H breaks off. The final product has the NO2 on it, and the H plus is off to the side. So in the end, all we've done is replaced an H that was on the molecule with an NO2. That's why it's called substitution. The thing that was substituted on is something that likes electrons, that's positive, that accepts electrons. That's why it's called electrophilic substitution. And so the mechanism is sort of like an SN1 mechanism in a way. It's also a little bit like an electrophilic addition reaction, but 2 arrows, 2 distinct steps, and a carbocation intermediate over here. So key things, make sure your arrows are correct, that they go from the ring to the N, from the bond between C and H to the dotted ring, and make sure that the carbocation intermediate has that dotted broken up ring with the positive sign. Those are going to be the key things for the marks. Okay? And it's a 2-step mechanism, so a potential energy diagram would have a high first step, and then it would have a lower activation energy second step. The breaking of the delocalized electron ring that happens in the first step has a high activation energy. So the key would be showing that the activation energy of the first step is bigger than the activation energy of the second step. So this is what's called the rate determining step. And it's a two-step mechanism. So two mountains of activation energy to get over. And that's the electrophilic substitution reaction of benzene.